Welcome, everybody. Thank you for coming to the CSP seminar. We have Nick Dork visiting us today. He's originally from California and did many different educational institutions in California, ending up with his PhD from Stanford University in electrical engineering, working with John Pauli, which is a name many people know. And he did a postdoctoral appointment at UC San Francisco. And finally left California. Let's see, is it 4 years ago now, I think?
Two and a half.
To go to the University of California, Anschutz, which is associated with, well, he's got multiple affiliations. He works with the math department, UC Boulder. His research gets routed through University of Colorado, Denver. You could say more if you want about the Anschutz campus.
Thank you.
Talking about accelerating MRI.
Thank you. And thank you so much for the gracious welcome. It was far more than I ever could have expected. Today, I'm going to be talking about novel technologies for accelerating MRI. This is where I work. This is basically the view from my office. Those are the Rocky Mountains in the background. That's downtown Denver in the distance. This is the Anschutz Medical Campus. It's part of the University of Colorado system. And on this campus, we have, here are 2 hospitals, but there are at least 3 hospitals. University of Colorado Health is the adult hospital, Children's Hospital Colorado, and then there's also a VA hospital on the campus as well. Sure. Does this change anything? Okay. So great. So this is where I work. It's a lovely place. I'm very grateful to be there. In the Children's Hospital Colorado, there's the Colorado Fetal Care Center, and it tries very hard to find ways to treat fetuses very well. And so one particular condition that we're interested in is called placental accreta. Usually due to a previous cesarean section, the placenta erroneously grows into the surrounding mother. And it can be extremely dangerous. It's the #1 cause for emergency hysterectomy. And worldwide, about 1 to 2% of women with this condition will die. Generally, what happens with these emergency hysterectomies is that the accreta was underdiagnosed. The severity of the accreta was underdiagnosed. So when the woman goes to give birth, when she delivers the placenta, it'll basically rip out quite a lot of her, and she starts hemorrhaging blood quite a lot. And so there's the emergency surgery, right? So mild accreta resolves with birth. The placenta delivers, maybe there's a little blood, maybe not, and everything's fine. Moderate accreta, there's starting to be experimental surgeries where they could cut out where the placenta has attached to the mother and just leave it there, but it doesn't require a hysterectomy. She could become pregnant again. Severe accreta requires a complete hysterectomy, and the woman's no longer able to get pregnant. So it's very important that we diagnose this condition accurately, that we stage it accurately. This is what it looks like in MRI. So this is the fetus's head up here, and this is the placenta going into the surrounding mother. Okay, so it's challenging to image the placenta. We want to know exactly like how much it's attached to the surrounding mother. And so the fetus is basically a continuously moving thing. Whereas a young child, you could sedate it. You can't sedate a fetus, right? So we want to scan in such a way that it's robust to motion artifacts. And one way to do that is just to collect less data. A very like robust way to do that is to collect less data and see. And if you can make a high quality image with less data, then you've got a faster scan. Provides less opportunity for motion, right? So here I'm going to talk to you about 4 different ways that maybe we can use to reduce the amount of data that we need for a high quality image. And the first one I'm going to talk about is sampling with a non-rectangular field of view. Okay, so how does MRI start? The patient lies in the bore, you put him in the machine, and the technologist generates a localizer scan. And then what does he or she do? Well, maybe he draws a rectangle around the patient. And then this rectangle dictates what we call a fully sampled pattern, where the data lies on a Cartesian grid, and the spacing between data points is the inverse of the corresponding distance of the rectangle that was drawn, right? This is what we call fully sampled. And you do it in both dimensions, X and Y. And so here, for this Cartesian grid, I'm imagining that each of these points is a line of data in the third dimension. So it's two dimensions of phase encodes, one dimension of readout. Okay. So if you have 256 by 256 grid with an 8 millisecond TR, you're looking at about 9 minutes of scan time. And that's quite long. So this is what we hope to reduce, right? And it seems a shame that we would need that amount of data for this image, because a quarter of this image, we know before we scan that there's nothing there. So we should be able to take advantage of that. Can we have a technologist draw something other than a rectangle around our patient and collect less data and still generate a high quality image? I'm going to show you that we can. The question is, what sampling pattern do we use? How do we reduce the sampling pattern based on this non-rectangular field of view? Okay, so what happens if I were to reconstruct this image only with every other column of data shown? So I'm going to take away half of the data. Any ideas? I know, what's that? Yeah, you get aliasing. So I'm going to delete the columns and I get aliasing. So here I've eliminated every other column and we've got aliasing. Do you notice that some of this image looks great? Right? Let's isolate the top half of this image. And now let's intersect it with this non-rectangular field of view. And we've got a pristine image of the leg. We only used half the data. Okay? What's left over is the foot. This turns out to be my foot. I find it kind of awkward that I've lectured a lot about my foot. Okay, so what sampling pattern do we need here if we're going to do the same approach, right? Well, the horizontal spacing will be the same because the horizontal distance was the same, but the vertical field of view is less. So we could separate the samples out vertically more, right? That's what we would need to satisfy Nyquist sampling if we were just going to recreate the image of this foot, right? Now this sampling pattern on the right, where the vertical spacing has increased, has fewer samples than this one that we were calling the fully sampled pattern earlier, right? And this does satisfy Nyquist for the foot, right? But Nyquist provides a lower bound on the number of samples that you need. So we can increase the number of samples over this blue dotted pattern, and we'd still satisfy Nyquist, right? So that's what I'm going to do. I'm going to replace every other column of this pattern with every other column of that one. Okay? So I'm going to remove every other column of the blue. I'm going to replace it with every other column of the gray. This is the sampling pattern we're going to use. And for the example of the foot that I showed you, this means taking every other column and every other row. So this is what that looks like. If you zoom in on this, we're taking every other column and every other row, and every 2 by 2, there's one missing. So I've reduced the number of samples by 25%, right? Okay. I use every other column. I reconstruct the image of the leg. Now I'm going to take the discrete Fourier transform of that. I'm going to subtract away those values from all of the data. And what's left is the DFT of just the foot, right? I'm going to inverse Fourier transform that. Take just the lower portion. Now I've got the leg and the foot, and you add them together, and you get a leg foot. Okay, so this is the fully sampled reconstruction. This is what happens if you just take the inverse DFT with zero filling. And here's the reconstruction with the non-rectangular field of view, 25% reduction in the number of samples, and a negligible difference to the quality of the image. This can be generalized. Now I'm going to show you how. So what I just showed you was retrospective downsampling. I eliminated data and then I compared the results. Now I'm going to show you prospective downsampling, okay? So this would be the localizer image if you wanted to scan a pineapple. This is the support of that pineapple where the image is non-zero. This particular experiment was delicious when we were done, so that was kind of cool. Okay, so if we did the same thing, if we got the quote unquote fully sampled pattern required by Nyquist according to a rectangular field of view, and then used just every other column to reconstruct this image, you'd get some aliasing. That's what that aliasing looks like, okay? Now I'm gonna remove any row where the aliased image overlaps itself. And this we know just from the support. We don't know anything else, just the non-rectangular field of view, the boundary of this white region. So I'm gonna eliminate those rows, okay? Now I'm gonna intersect that result with the non-rectangular field of view. That gives me this. So this is the pristine part of the image after I only use every other column to reconstruct. So here's our non-rectangular sampling pattern. We're going to use every other column to reconstruct this picture of the pineapple. That's what you get. You then intersect that with the outer region that we just identified. And now we have a pristine outer region of this pineapple. Take the DFT of that, subtract it away from the data that we had collected. All of the data that we collected, we're left with the DFT of just the inner portion of the pineapple. Inverse Fourier transform that. You get the inside of the pineapple. Add the two together, and you get the pineapple. So this is now prospective undersampling. On the left is the fully sampled reconstruction. In the middle is the non-rectangular field of view, 87% of the samples, and on the right is the difference multiplied by 4. So this does very good. So this is with a single coil here is what I've shown so far. Okay, so now we've answered the question. A technologist draws some arbitrary shape that they're calling the field of view. What sampling pattern do you use? Use this very fancy sampling pattern of gray and blue dots. So that's single coil imaging. What about parallel imaging? So some work has been done by this. So the paper POC-Sense, published by Samsonov et al., proposed it this way. They're going to minimize an optimization problem like this. So the top here is the data consistency. The image is X. S is a block column matrix of the sensitivity maps. And then F is going to be the non-uniform discrete Fourier transform, right? So you want the data, the Fourier values of the image that you reconstruct to match the data that you collected, which is P. That's what that objective function says, right? Okay. The bottom here is an indicator function. This says any pixel in X that's outside of the field of view should be 0, right? That's what that says. Okay. So how do you solve this problem? You could use projected gradient descent for this, projection gradient optimization, where it iterates over just calculating a gradient descent step and then doing a projection. So this projection here simply takes Y, the image Y, and everywhere outside the field of view, it sets it to 0. What do you think? Is this a reasonable thing to do? Yeah, I'd say it's a reasonable thing to do. I think there's something ever so slightly more reasonable. Here's an equivalent problem. We don't need this constraint. X here is just the pixels inside the non-rectangular field of view. M is the matrix that takes the full image and just returns those pixels that are inside the non-rectangular field of view. So M transpose puts the values of X into the right spot in the image, and everything else stays 0. This seems good because this is just a least squares problem. You could solve this analytically on some computers, right? For small enough problems. For larger problems, you can use LSQR, which is basically conjugate gradient. This is much faster than projection gradient. And though I presented to you this with the idea of using this particular sampling pattern that I've created from the non-rectangular field of view, this could be done with any sampling pattern, really. Okay. So here's now parallel imaging combined with the non-rectangular field of view using the sampling pattern that I created, but I've also eliminated every other sample from both the blue and the gray columns. So total reduction from fully sampled to 45% of the original number of samples. This is the original actual slice of pineapple. This is the This is the new parallel imaging reconstruction. This is the difference. So we're getting a good quality image with now a significantly reduced number of samples.
Can you clarify why it's the same sampling pattern for the planet? Foot at the scale.
Oh, no, it's a different sampling pattern between the pineapple and the foot. Yeah, no, it's not. So I just meant that the blue dots are separated by the inverse of the distance of the inner portion with a pineapple.
Oh, but if it's same family of sampling.
Yeah, let's say family. Yeah, same family.
This is the persistent pattern.
Yeah, right. Yeah. Yeah.
Not necessarily the best thing, but one that's.
Definitely. Yeah. So perhaps you're thinking you could combine this with compressed sensing, but then with compressed sensing, you'd want to do some sort of random sampling, let's say. Okay. So with some compressed sensing, you might generate a random sampling pattern, but then you also want the data to lie on a Cartesian grid because that's convenient sometimes. Okay. So here you could do the same thing, but instead of moving samples to a Cartesian grid, you move samples to this irregular sampling pattern that I've created. That's the idea. I haven't done that yet. Okay, so that's acceleration with a non-rectangular field of view. Now, in front of Dugnall, I'm going to talk about homodyne detection. That's actually going to happen right now. Okay, and I'd like to acknowledge my student, Alex McManus, who was the driving force behind most of this work. First, we're going to discuss compressed sensing. Here are 5 different images. These are some of them. Oh, I see. Yeah. Okay, so compressed sensing relies on the fact that if you transform these images in some way, then the result is approximately sparse. So here's the Debouchet discrete wavelet transform. And you notice that it's approximately sparse. These images are well represented by a few coefficients, represented by the sort of brighter pixels in each of these images. It's mostly black. If you ask an 8-year-old, like, what do you see here? They're going to say that's mostly black, right? That's the point. The wavelet transform of images, natural images, is mostly black. And that's what compressed sensing exploits. Here's how. It's a constrained optimization problem. This is data consistency. This says, if you get the right image X, Fourier transform it, and then look at the data that was collected, look at the spatial frequencies that were collected, it should match the data you actually get well, right? The other term says basically that the wavelet transform of the image X should be sparse, right? Okay. And so how does this work? This is a variable density sampling pattern with 33% of the samples, though for convenience, I moved the samples onto a Cartesian grid. And then, and this is the reconstruction. So this is absolutely amazing, right? Like a revolution in MRI. 33% of the samples, 3 times faster, high quality image out. There's a separate technology, partial Fourier. If the image were real, like what's the Fourier what can you tell me about the Fourier transform of a real image? Oh, I guess you could see it right. You could just read it right here. If the image were real, then its Fourier transform is Hermitian symmetric. If it's Hermitian symmetric, it means you only need half the data. Okay, so here's a full example reconstruction of a sagittal slice of a knee. And this is what happens if we pretend that the image is real and then fill in half of it with the conjugate symmetry. Okay? It's bad. It's not that good. Why? Because MRI images aren't real. Why? Because B0 is not constant, because B1 is not homogeneous, right? So it's not quite real. So what do? Doug? Okay. We can use homodyne detection. So the image is not real, but we assume that its phase is low bandwidth, which is a very good approximation. And so this is 63% of the samples, and this is what we get. How does this homodyne detection work? Here's a flow chart describing the algorithm, and I'm going to go through this sort of step by step. So you sample slightly more than half of K space, maybe 5/8, maybe 9/16. Yeah? You look at just the center of K-space, and you assume that the phase is contained within a center region, a low-pass filtered image, a low-pass filtered version of your image. You reconstruct the image and estimate its phase. Okay? So now we're down here. We're going to go back to the top. This is our slightly more than half sampled K-space. We're going to multiply it by a ramp, this ramp, that smoothly transitions from 2 down to 0. Multiply them together, take the inverse discrete Fourier transform, then multiply by the phase that we estimated previously, take the real part, and we get out this nice image. So that's a very high quality image, 5/8 of the sampling pattern. How'd I do? All right. Okay. Yeah. If you take the real part of the data multiplied by that pre-weighting function, you end up with you could decompose that weighting ramp into 2 different components, one that's even, one that's odd. The even part is constant, and that's what you end up getting out. So I highly recommend this paper by this author, Douglas Knoll. Oh, or we could talk about it more afterwards. Okay. So how is partial Fourier, this idea that we could collect, slightly more than half, combined with compressed sensing? What's the state-of-the-art method of combining partial Fourier with compressed sensing? They take the variable density sampling pattern of compressed sensing, right? And they eliminate the lower portion. So they take maybe the top 5/8 of that, and then they solve it with compressed sensing. And that's it. So what happened to homodyne? Where's all that processing in the flowchart that I just showed you? It's not included right now. It's not included in the state of the art right now. Okay, so here's the flowchart. And what we realized is that once you estimate the phase from the center of K-space, once you call that your phase, the rest of this is just a linear transformation, a single linear transformation that inputs the top 5/8 of the data and outputs an image, okay? Let's call that linear transformation P. So now I'm going to modify the compressed sensing problem. This is what we're calling compressed sensing with homodyne. How does this work? This says take Y, which is now just the top 5/8 of K-space. Apply the homodyne reconstruction operator P. That gives you an image. Take the wavelet transform. That gives you something sparse. So we want to minimize the L1 norm of that. We want to make that result sparse, the wavelet transform of the image. And this says, take the top 5/8. M says, isolate only those samples that were actually collected, compare that to the data, make sure the L2 norm of the difference is small, within epsilon. And so intuitively, what's happening is we're using sparsity now just to fill in the top 5/8. And we're using the homodyne detection, the homodyne assumption to fill in the rest.
What is P again?
P is the homodyne reconstruction operation. So let's see how it works. Oh, and this problem can be solved with the primal dual hybrid gradient method. This is single coil, yeah. Right, it's single coil. So on the left is the current state-of-the-art compressed sensing plus partial Fourier. This is with 17% of the samples, which is usually more than you'd accelerate right now when combining compressed sensing with partial Fourier. And on the right is compressed sensing with homodyne. And I'll give you just a second to realize that the right's like way, way, way better. We'll zoom in and you see the lines are sharper. There are more details. It's a better result. Okay. Now I'm going to tell you about structured compressed sensing. We previously said that the wavelet transform of these images are approximately sparse, right? An 8-year-old could look at this and say, yeah, it's mostly black, and they'd be right. But the lowest frequency bins are not. We know that ahead of time. Natural images almost always, unless the natural image is sparse to begin with, the lowest frequency bin is not going to be sparse. So since we know it's not sparse and we know it's low frequency and we know its resolution, we could satisfy Nyquist for just that region, just the lowest frequency band of the discrete wavelet transform. That's this. And we can window this inverse discrete Fourier transform, and you come up with a very blurry image. Okay? What would happen if I took that blurry image, subtracted it from the original image, and then took the wavelet transform? This is that. And so if we now zoom into the lowest frequency portion, now it is sparse. Now the entire wavelet domain is sparse. So I wanted to take advantage of the structure of the wavelet transform, where when I know this lowest frequency bin is not going to be sparse. I modified the standard compressed sensing problem to do that. So what does this say? Y hat L, those are that low frequency region, that Nyquist sampled region, fully sampled region of K-space. You can apply a window to that to eliminate ringing. Here I'm applying a Kaiser-Bessel window. Then inverse Fourier transform that's the blurry image, right? And what I want is for the actual image Y, subtracting away the blurry image for that to be sparse, okay? So that's what this is. So I'm going to minimize the L1 norm of the wavelet transform of the blurry image subtracted away from the hypothetical correct image. By minimizing the L1 norm, we encourage sparsity. This again is just the data consistency term. Now I'm going to do a very simple variable substitution. That gets us to this problem. And this problem is interesting because it's almost the exact same thing as the original compressed sensing problem. The only difference is that this vector B has been replaced by a different vector beta. Okay. So you could use the same code to solve it. I actually call it, like, inside my structural sparsity code, I call my compressed sensing code. The sampling pattern needs to be different, right? This is 8% of the samples, 33% of the samples. This is a variable density sampling pattern. This has this fully sampled region dictated by the size of the lowest frequency bin of the wavelet transform, and then superimpose on that as a variable density sampling pattern, okay? These are the results. So these are comparable quality now. The bulk of the benefit is just from the alteration of the sampling pattern. Very little benefit comes from changing the optimization problem. But you do get ever so slightly some gain by changing this optimization problem. Now you might say, maybe I'm cheating. Maybe if I had used 8% of the samples for compressed sensing, it would look just as good, right? It doesn't. 8% is too far, too much acceleration for standard compressed sensing.
But that sample, that 8% is it's original sampling pattern that does not have a.
Right, it does not have a fully sampled. Yeah, if it had a fully sampled fully sampled region in the center, it would look much more similar to this. Yeah. You can combine this with parallel imaging. I just did this. So the S is the block column matrix that represents the sensitivity maps. Sorry, this is standard combination of parallel imaging with compressed sensing. This is now taking advantage of the structured sparsity. And again, the only difference is B has been replaced with beta. And again, the results are better. So this is fully sampled reconstruction. This is the reconstruction with structured sparsity. And this is the reconstruction with parallel imaging with compressed sensing, the standard reconstruction approach, both with 18% of the samples, higher detail, closer to the fully sampled reconstruction. Okay, so it's better. Lastly, I'm going to talk about data. Yeah, go ahead. right. Yeah, right. No, not yet. It's definitely on its way. Yeah,
I have a question. So
Sure.
about the central core piece of it. Now, if doing parallel imaging, in principle, you don't actually need fully fully sample central core because you're.
hmm
If you use fully sample, is it necessary?
That's a good question. It depends what you mean by parallel imaging. If you're using, for example, grappa, you need some fully sampled center region, right? Yeah, yeah. So maybe you're saying,
Yeah, like suppose you had sensitivity.
if you had sensitivity maps, yeah, then you don't. Yeah, so then you could accelerate even further. Yeah, that I actually have done. So I've not done the fully, how do I say this? I've undersampled the fully sampled center region and gotten an additional acceleration on top of that with a negligible difference to the quality. But I don't have that to show you today. Yeah, yeah. Okay, lastly, I'm going to talk about data consistent deep learning. This again, I'd like to acknowledge my student, Alec McManus, who did the bulk of the work. Do you recognize this, Jeff? Okay. This, yeah. This is one of my favorite works ever. Okay, so here's a fully sampled reconstruction image of a brain, and this patient tragically has cancerous tumors in his brain. I believe this was a testicular cancer that metastasized into the brain. This is a very uncommon pathology. This is what standard parallel imaging with compressed sensing gives you, and it's a very reasonable reconstruction, perhaps slightly noisier than the fully sampled reconstruction. And this is what a unit trained on a relatively large data set reconstructed. Ready? Boom. And so, as Jeff says, this was work by Gopal Nataraj. And so if we look at this smaller tumor here, the tumor's all been eliminated by the deep learning, right? It's just gone. And that's a problem. So what's happening? Well, we have this patient that we send into the MRI machine, then we collect a bunch of data, we undersample. So we have some undersampled sampling pattern of Fourier values, right? We send that through a neural network that we've trained. We've previously trained on a large data set. And then out comes this image. And so we can actually know this is bad. If we take the Fourier transform of the image and look at just the data points that were sampled, they wouldn't match the actual data that we collected. The reconstruction is inconsistent with the data. So this is the problem we're going to talk about now. This should be fixable, right? We should be at the lowest level of success for any reconstruction algorithm should be it matched the data that you gave it, right? Yeah, okay. So what the fundamental problem is that deep learning is trying to do two things. It's trying to match the data that you give it, okay. But it's also trying to recapitulate the features that existed in the training set. It's trying to do what it's learned. And those things can be at odds with each other. If we had a choice, right, we would always choose to match the data and then just choose to fill in the missing parts from the training, from what we've learned. So people have tried to address this. Oh, let me say one more thing. Here's another error that deep learning can create. So this is from CT image. Now on the left is what would be a fully sampled reconstruction, except, and this is work by Meyer et al. They've inserted a tumor. This circle where the red arrow is pointing is like a fictitious tumor. This is a zoom in that little region right there, okay? They undersampled CT, so they didn't send the machine all the way around as much as you needed, so they don't have all the data that would be required for a complete CT reconstruction. This is what happens if you do filtered back projection. Amazingly, the tumor's still not evident, but a whole lot of blurring here, right? Like you couldn't trust this image at all. This is what the deep learning reconstruction does. It actually moves the chest wall down to get rid of the tumor. because that's more in line with what it's seen in its training data. And you can see the tumors all but been eliminated here. Now, one way that people have tried to correct this fact that deep learning generates images that are not consistent with the data is to somehow take an average of an image that matches the data and the one that the neural network outputs, right? So this is what that might look like. And so you get significant ghosting, right? So this is not, in my mind, this is not a viable option. This is not a good idea. This is a strict definition of data consistency. If I take the image X and I multiply by the sensitivity maps, take the Fourier transform of each of those images, and then look at the spatial frequencies for the data that was collected, it matches the data within a noise bound. That's what this says, okay? So this is what we want. This is what every image of any reconstruction algorithm should give us. One way that people have tried to address this is by adding this term as a regularization term into the loss function that's used during training. And that seems like a very reasonable thing to do, right? It doesn't always work. This encourages data consistency, but does not guarantee it. And so here's one very good work by Nalini Singh et al., where they took this approach and they also, after the image was reconstructed, they looked at what the value was to make sure it was below some reasonable threshold. And then they say, when this loss is high, we discard the reconstruction and or decide to reacquire the image. So this is them saying that even though they included this in the loss function, they're still generating images that are not data consistent. So this doesn't solve the problem. It maybe helps, but it doesn't solve the problem. Here's another way that people have tried. Remember, I told you, the neural network tries to do two things. One is match the data, and the other is recapitulate the features of the training set. If you could embody that statement in an optimization problem, this would be it. This says match the data. This says make the result close to what the neural network returns. And so here they're taking some sort of matrix weighted average of two images, right? So this is going to be an example where you get something like the ghosting that I showed you previously. The result is a combination of two separate images, and when the result that the neural network outputs is not data consistent, the result of this is almost assuredly not data consistent for any meaningful lambda. Okay? Okay. Here's an approach taken by Hammernick et al. In another excellent work. I highly recommend this paper. You could think of this optimization function as you could think of the solution to this optimization function as a function itself, h, right? That is, you input x into h and you get a result, yeah? They took this function and included it as a layer in a neural network. And so this increases the cost of the training dramatically, because now you have to solve a convex optimization problem for each element in your training set. But you can do it. So let's call this soft data consistency, because there's now some data consistency term embedded into the network, but it's only soft. The result, it still creates images that are not data consistent. Okay. In the limit, as lambda goes to 0 from the right, so as lambda gets smaller, 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 this method leaves the collected Fourier values alone and just replaces all the other Fourier values with the corresponding values of the result that the neural network output. You don't need to do that by solving, finding the limit of an optimization problem as lambda goes to 0. This can be achieved with a post-processing step. You have your neural network, and then you do a projection. You do a projection, so you're going to take the result of the neural network, and you're going to do a Euclidean projection onto the set of data consistent images. What does that mean? You take the Fourier transform of the result that the neural network gives you, you replace the known values with the values that were collected by the machine, and then you inverse Fourier transform. So this is great because the result is data consistent. Like that's what we've been after the whole time. This was published very early. Like many prestigious works have cited this paper, but none of them have used this technique because it still has this competition between matching the training data and matching the data itself. So it still creates a matrix-weighted combination of two images, which can lead to poor quality results, which is unfortunate. This was almost great. This was almost right, in my opinion. Are you ready for the amazing trick? I included the projection into the network itself. And then I include it in training, or we include it in training. And so what happens? Now the result of the network is data consistent. And during training, the network learns how to interpolate missing values without changing the values that it knows. So it learns how to, we call it image formation, not fabrication. It's not making stuff up. It's interpolating where it should. Here are some results. So now I'm going to show you the results of a UNet trained only on knee data. So this network has only ever seen knee data. I'm going to show you 5% of the samples, reconstruction from 5% of the samples, okay? This is what the data inconsistent network does. So this network, although I say data inconsistent, it was trained with a data consistency term in the loss function. There's just not a data consistency, there's not enforced data consistency in the network itself. So this is what the data inconsistent deep learning network does. And this is what our new network does. And you are totally underwhelmed right now because these results are basically the same, right? Okay, let's look at a different example. Now we're going to look at a brain, okay? The same unit trained on only knee data. This network has never seen a brain, and we're only going to use 5% of the samples, okay? This is what the data inconsistent deep learning network does. This is what our new data consistent network does. Ta-da, right? Like, this was, I think this was, no. Okay. Here are other examples. So what I showed you before was a UNet. Now I'm going to show you results with a VARNet, variational network. On the left is the full reconstruction. And on the right is what the zero field reconstruction would be. And it's terrible, which is why we always compare to the zero field reconstruction, because everything looks good compared to a zero field reconstruction. This is with 25% of the samples. This is VARNet with soft data consistency. So they actually included that soft data consistency layer into the network itself, right? And again, this was trained only on knee data. And what you see is a hallucination. Can you see it very well? May I turn off the lights? Do you guys see the hole in the bone marrow? Can you imagine a doctor seeing this and believing it? Like maybe it's a tumor, maybe we need a biopsy, maybe we need to stick a needle into your bone marrow. We'd like to avoid that, right? Like that's a problem. All right, so the hallucination is a problem. It doesn't really exist. This is what the network does with our now projection layer incorporated into the network. As you can see, the hallucination is all but gone. It's almost completely gone. Far better than the data inconsistent network. We have another example. Here's another example. Similar sort of hallucination that all but gets eliminated with our data consistent network. So what's going on here? Consider the special case of data consistency. So now I'm just going to think about a single coil, even though I showed you multi-coil data a second ago. So you take X, you take the Fourier transform, you look at just the spatial frequency that were collected, and let's say not only it should be close to B, but it should be exactly B. Okay? consider the hallucination H. So the result X is the true image XT plus the hallucination. We could distribute, right? We could just distribute df across x, where x is equal to xt plus xh. That gives us this, df xt plus df xh equals b. But this is right. B is, we know, the 40 samples of the true image. Those are the values that were collected. So we could subtract df xt from both sides, and you get df xh equals 0. So what does this say? This says that the hallucination is in the null space of our system matrix, right? Suppose that A has what's called the restricted isometry property of order S. So this is like a fundamental property related to compressed sensing. Intuitively, it means that A is close to orthogonal in a very formal definition, in a very formal sense. If A is RIP, then it has the null space property of order S. And what that says is that anything in the null space cannot be too small, and it cannot be too concentrated. And so we know that the hallucination has to exist in the null space of the system matrix. So for a given hallucination, its energy must be spread if A is RIP. So by including this data consistency term, we think we're very close to a proof that we've bounded the impact of local hallucinations, meaningfully eliminated local hallucinations, some statement like that. Okay, what have I shown you? I've shown you how to take advantage of a non-rectangular field of view with a novel sampling pattern. I've shown you how to combine compressed sensing with homodyne detection. I've shown you how to take advantage of structured sparsity. And I've shown you how to impose data consistency into a deep learning network to eliminate local hallucinations. What does the future look like? We're gonna slam all of this together, right? That's our immediate and future work. Thank you for your attention.
Building this up.
That's a good question. Yes. Yeah. Two. Yeah. Not some, but let's say union, the union of two rectangles. Yeah. Yeah. Right. Yeah. Yeah.
See that more easily through the day.
Right. So if this is the pineapple, the field of view that we're actually like something like this. I'm a terrible artist, but yeah. So if this cross were totally filled, we'd have the same sampling pattern as we got for the pineapple.
So I have a question.
Yeah.
So I saw your sample number is still reduced, but it doesn't necessarily mean that actually accelerate the actual acquisition, because sometimes, I mean, in the readout direction, you just reduce the number of samples doesn't really contribute to the reducing the time.
So here I've reduced the number of readouts. Yeah.
In 3D.
Oh, it's in 3D.
Yeah.
I mean, you're showing us 2D images, but you're planning to apply this in 3D, right?
Right. And so it's been applied in 3D. I've shown you slices, but yeah.
Last week it says.
Sorry, I couldn't.
Sorry, or in the last sentence of the show, that where you were reading the hallucination.
Yeah.
And you were new layer. Did you do that experiment you mentioned where you go back to
Don't have to, because we're guaranteed same value. There's no, the answer is 0. There's no difference there. Yeah.
I'd like to come back to the multi-coil. It's trivial to do the projection in the single coil case, you just replace the.
Right, right.
Sure, off the top of my head, now you do the projection in the multi.
Right, and what does it mean to project in the multi-coil case? So a generalization of projection is the proximal operator. So I'm just solving the proximal operator.
That's an iterative step.
So, right, so this is why I was saying, like, if you just sort of do it naively, then, then what? Then you have to solve a convex optimization problem for every element in the training set. But so we didn't do that. Instead, we did a projection on each coil image individually and then combined them using the method of Romer et al. And then we're calling that an approximation to the solution. And that was actually published as, I just saw on the way here actually that this technique that we came up with on the fly is part of the Samsonov Poxens paper. That's how he did it as well.
So the Romer combination uses sensitivity.
It does, yeah.
So, one more point, going back to your original introduction where you talked about. You know, calibration.
No, I'm much more interested in grappa spirit like techniques that don't require sensitivity maps. Yeah,
So,
yeah, right, yeah. Thank you.
so thank you. That's all.
You're welcome. Thank you.
Question. So sometimes I think of like this weighting, the ramp function, weighting function in sort of like a density compensation function,
Okay.
you know, implemented in such a way as to prevent rigging or be robust in some way. And then so I was intrigued by, and so working with Jeff for quite a few years, we've been doing like non-Cartesian sampling, reconstruction. There's always this debate whether or not to include that's not much of a debate. Otherwise, whether or not to include the density compensation function in the data fit term or and the argument against doing it is that you might prime the network by using it, but then after, or prime the reconstruction by using it, but then not use it because it's you make an argument that its noise properties are best if you don't use it inside the cost function. And so I'm just kind of, I don't really know, I don't know if this is a question or not. I'm trying to figure out whether or not, and so in your implementation, I'm wondering if it will work without the weighting function, but with the projection into the real space or whatever. You know, that is whether we converge to something very similar. I guess it's sort of, I don't know if that question made any sense or you know where I'm going.
Question makes sense. If it were a legitimate question, I might ask you, what do you think will happen, Doug?
I think it'll work.
Okay.
So it wasn't really a question.
Okay. Suggestion maybe. Yeah. Okay.
The instruction sparsity side by side. Many questions, and you and I can talk more later. This is one I want to ask. Let's do it just on that. So I believe I'm seeing wavelet artifacts in these.
Okay. Yeah. I'm sure you're right.
Due to the soft thresholding, right? So there's, I think you've got one norm floating around, right?
Sure. Yeah.
So it's more dramatic than I'm used to. I don't know how much of it's the projector, so can you point with your cursor, what do you think I'm talking about, or I can come up with?
Like anywhere? I could basically point anywhere? Yeah.
What do you plan to do about it? Assume that would not be, I mean, it only depends on the application, whether subtle details.
Right. Yeah, right. A couple of things. One is, so we're using the L1 norm right now as the sparsity thing. sparsity, what do you call it? Objective function. And that the L1 norm induces like actual sparsity, values go to zero. But we know that our image, our true image has Gaussian noise. And so you wouldn't expect the wavelet transform to be actually sparse. You'd expect them to have values that are within the noise bound. And so there's already a way to deal with this, the Huber penalty. So we're going to replace the L1 norm with the Huber penalty. And maybe that'll help. I've also combined this so here I'm showing you just the wavelet transform, but I've done this with what do they call it? An overcomplete dictionary using both the wavelet and curvelet transform. And you could extend that out as much as you want, right? You could add as many dictionaries into that as you want. That'll help eliminate this a little, I think.
In fact, although I see the individual wavelet pieces, I don't see log boundaries I might have expected from log transform. So what actually?
It's orthogonal. It's the Debouchet discrete wavelet transform of size 4.
Expecting to see something every in over 200 form.
I don't usually see that.
I was under the impression that many of the commercial compressed sensing methods also throw in a little bit of TV. Yeah, that is sort of just a wavelet plus a little TV.
I've seen that for dynamic reconstruction.
No.
Yeah, that who does, right? Yeah. When I've seen TV used still, I see it like wavelet sparsity in the spatial domain in the spatial dimensions, and then TV in the temporal. Sure. Yeah.
I was gonna ask the same thing, because you're setting it up as minimize one norm of the subject to a data consistency less than epsilon.
Mhm.
And so that's not just didactic, that's the way you're actually solving it, as opposed to minimize a weighted sum of the two. Which
Yeah.
makes it easier to have TV, it's just another regular row, right?
Right. I mean, we could do that here too. I like this much better because if you do the weighted sum, what's the regularization parameter?
So you're gonna tell me epsilon, but go ahead, tell me.
You scan without any excitation. That gives you an estimate of the noise bound there. So yeah, okay. So
But if you want to throw in TV, then you will need a regularization factor, because you'll have to balance wavelets.
I mean, it'd be questionable why you would do that because TV is like you're penalizing the norm of the first order difference, right? First order difference is like a high pass. Yeah, right. Yeah, there you go. Yeah, yes. Okay. So we're already penalizing that in a sense, and yeah.
But I never liked it.
Hey, thank you everybody very much for the welcome and for the time that you spent with me today. I really, really appreciated it. I had a great time.
So I said, well,